Hello, Physics 20s. We are starting a new unit. Well, we already started it the day before your exam when we did that little stations activity. Today we're going to do a little bit of notes on some of Newton's laws of motion. So this is your new, you should have your new notes booklet with you. This is Unit 2. It's called Dynamics. Again, it's like the kinematics unit. It's just in one dimension. The general outcome that we're going to cover in this unit is students will explain the effects of balanced and unbalanced forces on velocity. And that's basically all we're doing in this unit, is just looking at forces, situations where forces are balanced and forces are unbalanced. The key concepts that we're going to develop through the unit are Newton's laws of motion, the concept of inertia, which is related to Newton's first law of motion, static and kinetic friction, what friction is and what the difference between static and kinetic friction is. And then we're also going to do some vector addition of forces. So on the next page in your notes is the unit outline. And I did actually recognize that I made a mistake here because I have us reviewing on Monday, March 16th, when in fact that's a staff meeting PD day, so there's no school that day. So this is going to be, we need to change this to Tuesday, March 17th, and then change the exam to Wednesday, March 18th, and I've made those, I've put the correct dates, whoops, sorry, that should be the 18th. I've put the correct dates on the board. They're up there now for you. Okay, so then we want to begin on page 3, and we've got this whole whack load of outcomes we're going to go through and color a little bit. So the specific outcomes that we're covering in this particular lesson, it seems like a lot. We're going to look at all 3 of Newton's laws. So we want to explain that a non-zero force causes a change in velocity. So that is a green outcome. Okay. Apply Newton's first law of motion to explain qualitatively an object's state of rest or uniform motion. So apply and explain are both green. Apply Newton's second law of motion to explain qualitatively. So qualitatively, remember, means with words, the relationships among net force, mass, and acceleration. So apply and explain are green. Apply Newton's third law of motion to explain qualitatively the interaction between 2 objects, recognizing that the 2 forces, equal in magnitude and opposite in direction, do not act on the same object. And then apply Newton's laws of motion to solve algebraically linear motion problems in horizontal and vertical planes near the surface of the Earth. And we're going to generally be ignoring air resistance most of the time for vertical. So just like with kinematics, we're going to look at both horizontal motion, just motion in a horizontal plane, and motion in a vertical plane. Okay. What you need to be able to do from those outcomes is, first of all, define force. Okay, so that's just a yellow outcome. That's a knowledge, just repeating what I'm going to tell you. We want to classify force as a vector quantity. You need to be able to state Newton's first law of motion. And related to Newton's first law of motion, there's a standard of excellence outcome here, where you're required to communicate that inertia is not a force that keeps objects in motion, and a force is not required to keep objects in motion. That notion of that a force isn't required to keep objects in motion is a really difficult concept to wrap your head around sometimes. State and apply Newton's second law of motion to explain qualitatively the relationships among net force, mass, and acceleration. So the state is yellow, like telling me what Newton's second law is just a memorized thing, but applying Newton's second law is actually comprehension and application. Solve for any variable in the 2 formulas related to Newton's second law that we're going to look at. So acceleration is F net over mass, and acceleration due to gravity is the force of gravity divided by mass. That's as far as we're good. Define normal force. We're doing that on Monday, but I've got the one outcome here. Relate system international units to physics quantities. So we're going to look at force being measured in newtons, which is also kilogram meter per second squared. All the normal force stuff and Newton's third law stuff we're going to look at on Monday. I don't want to cover too much today. Okay, so on to the next page. And we're just starting here. So this unit I said was called dynamics. Kinematics, the first unit we did, was how objects move, right? Like we looked at how objects move, so we analyzed like velocity, displacement, time, acceleration. Dynamics is the study of why objects move. And it's based on Newton's laws of motion. Okay, so I said that dynamics is the study of why objects move. It's based on Newton's laws of motion. And what we basically do when we study dynamics is we're analyzing the forces that act on an object in a system. So that's sort of the purpose or why we're doing it. So we analyze the forces acting on an object in a system. Okay, so then what that does is that leads us to the question, or sort of the idea of what is the force. And the force is simply a push or a pull. And in physics, we can have contact forces, which is what we're generally talking about in this unit, and non-contact forces, which come up in later units. The difference being a contact force that requires, like, it's a push, you're constantly pushing on something, or you're pulling on it, like you're making contact. There's contact between what's applying the force and the object that's experiencing the force. Non-contact forces are forces like gravity that act over space with no contact between the object and the object that's moving and the object that is causing the force. So force is a push or a pull on an object. A force can change the velocity or the shape of an object. It is a vector quantity. So that means it has magnitude and direction. The symbol for force is a capital F with the vector symbol above it. So that is how we symbolize force. In terms of unit analysis, and I'm kind of doing this, in order to do the unit analysis for it, I have to kind of introduce the formula before I've really introduced it to you. But force is measured in newtons. Which is given the capital letter N. So our formula for force, or what you would have talked about last year, we actually state it in a slightly different way later on in this lesson. But the formula that you would have learned last year for force is F net is equal to mass times acceleration. And so we have, if we know that force is measured in newtons, okay, we're going to do a unit analysis to see what a newton is actually made up of by looking at what makes up, what units make up mass and what units make up acceleration. So it's pretty straightforward. Mass is kilograms, acceleration is meters per second squared. So 1 Newton is equal to 1 kilogram times a meter per second squared, which means 1 Newton of force is the force that's required to move 1 kilogram at an acceleration of 1 meter per second squared. So before we get more specifically into some of the laws, we'll just generally define all three of Newton's laws of motion. And there's a number of different ways it could be stated. So through these notes, I'm going to kind of state the laws in different ways. And you find the way to describe the law yourself that makes the most sense to you. So Newton's first law says that an object will remain in a state of rest or constant velocity remember, rest and constant velocity are considered to be the same thing. So that means uniform motion in a straight line unless acted upon by an unbalanced force. It's sometimes called the law of inertia. We'll talk about what that means and what inertia is in a few minutes. And when we talk about Newton's first law, we're just talking about a single object. So Newton's first law is sometimes the hardest one to actually recognize what's going on. It used to be thought that in order for an object to be moving, there had to be a force acting on it, and that there was a force inherent in the object, things like that. But what the first law is saying is that if you, in the absence of any outside force, so if there was no friction and you rolled a ball on the floor and the floor was totally frictionless, that ball would keep going indefinitely until something stopped it, until it ran into a wall. There's no wall for it to run into, it would just keep going forever. Newton's second law says that when an external non-zero force so what that is an unbalanced force acts on an object the object will accelerate in the direction of the force. Okay. And it's the law that carries with it a formula. And the formula, as it's written on your formula sheet, is that acceleration is equal to F net divided by mass. And the reason why it's written that way and not the way that you learned it last year is because it's a net force that causes an acceleration. So that's shown in the formula, right? Like we've got, you plug in some value for F net for mass, and that'll give you the value of acceleration. So the formula is showing how acceleration changes for changes in net force. When the formula is written the other way, what that's sort of implying is that acceleration causes a net force, and that's not the correct way of thinking about it. Newton's second law as well is only for a single object. Newton's third law, and it's probably the one that most people remember, it's for every action there is an equal and opposite reaction. I'm going to sneak in here, for every action force, there's an equal and opposite reaction force. And this is the one, the third law, we're talking about two objects. When we're talking about the third law, we're always analyzing forces on two objects. So we have to look at the forces in two separate calculations. So we'll focus on the first law first. So Newton's first law, which I said was called the law of inertia, it just, the simplistic way of stating it is an object at rest stays at rest. An object at rest stays at rest, and an object in motion stays in motion until acted upon by an external force. It's referred to as the law of inertia because of what inertia is. And inertia is the resistance to change I'm going to change that. Inertia is an object's resistance to a change in its motion. So, like, it's really a property that's related more to mass. The more mass an object has, the more inertia it's going to have. It's a lot harder to push a car out of a ditch than it is to push a bike out of a ditch because the car has much more mass. So that's inertia. So all objects possess inertia. Objects with greater mass have more inertia. They're harder to move. So a consequence of Newton's first law is that whenever something's traveling at a speed, at a certain speed, it requires a force to stop that object from traveling. And so then that leads us to talk about situations here where objects or else, people are traveling in objects that are moving, and what happens to them. So if we look at it, I've just got a couple situations here that we're going to kind of talk about here, and I want you to think about your own experiences, or if you have experiences in terms of how, if these things happened to you, how you felt when they happened. So we're just looking at, we're going to describe what would happen to us if we were in these scenarios. So the first one, we're standing in the aisle of a school bus that's traveling at 50 kilometers an hour. So you're standing in the aisle. I mean, you could do this for sitting as well. Standing in the aisle is just a better visual. So if you're standing in the aisle of a school bus that's traveling at 50 kilometers an hour, and the bus driver is going to brake hard. So what I want to stress here is that everything in the bus is also traveling at 50 kilometers per hour. Okay? So what happens then, if everything in the bus is traveling at 50 kilometers per hour, everything in the bus is traveling at 50 kilometers per hour, when the bus driver brakes, anything that's not tied down will continue traveling at 50 kilometers per hour. So that means if you're standing in the aisle, you will keep moving forward at 50 kilometers per hour until stopped by an external force. Right? And everything else that's not tied down in the bus will keep moving, right? So if there's a ball sitting on the ground, it's going to keep moving too until it's stopped front. So same situation, you're standing in the aisle of a school bus traveling at 50 kilometers per hour when the bus suddenly turns to the right. Okay, and this is a weird one because your first inclination is to say you move to the left. That is the physical perception. The thing is you don't actually move to the left. You stay right where you are, the bus keeps turning. So you stay where you are as the bus turns. Okay. And that feels like you move left. And this will occur until you are stopped by an outside force. So whatever state of motion an object is in, it will continue in that state of motion until something pushes on it or pulls on it and creates a force to stop it. Okay. Okay, so another situation. You are traveling in a vehicle that's moving at 100 kilometers per hour. The car comes to a very sudden stop. So imagine hitting a brick wall. Okay, so it's just going to stop as instantly as it can. So what happens to you if you're not wearing a seatbelt? Okay, since you are traveling, you are also moving at 100 kilometers per hour. You will continue moving forward at this speed until stopped by an outside force that will be something like the windshield or more likely the brick wall. And this is why we wear a seatbelt, because that seatbelt applies an external force to prevent you from getting hurled outside of the car. So the same is true of any objects in the car that aren't tied down. So let's say you're in a car that actually has a back window, with a ledge on the back window, and that's where you've decided to put your laptop. When that car that was going 100 kilometers per hour comes to a sudden stop, the laptop continues moving forward at 100 kilometers per hour until stopped by an external force, like the windshield or the brick wall the car hit, or perhaps the back of your head. So you want to be careful what kind of stuff you have in your car when you're driving, because it will move around. It will keep moving around at the speed that you're going until it gets stopped by an outside force. That's why all of a sudden, like in about the last 10 years, it's become like there's been a little bit more push to tie animals down. Like when I was young, we used to drive around with our puppy in the car all the time, just sitting on my dad's lap or sitting on my lap or walking around in the car. But, you know, if we'd ever been in any kind of accident, the dog would have just gone flying. All of us were tied in, but that dog was not going to be happy if anything had ever happened. What happens to you if you're wearing a seatbelt? Well, the seatbelt acts as an outside force, or the seatbelt provides an external force to slow your body down and prevent injury. That's about the best way I can put that. You know, so, and it's actually the seatbelt and the airbags that work in tandem to really slow you down over a long period of time, or like over a, like to decrease the amount of force that your body's feeling over a long period of time. So that seatbelt is what will keep you from going through the windshield and hitting whatever it was that stopped the vehicle in the first place. On to the next page. You guys can stop and start this as much as you need to. So part C, you are a passenger in a car that accelerates quickly from 0 to 100 kilometers per hour. What happens to you? Well, you're just pushed back into the seat. Right? Your body is pushed backwards. Into your seat. And that's from your body's inertia. You're sitting there at rest, all of a sudden the driver nails the gas, your body wants to stay where it is, but so it's kind of, the car moves forward, your body stays where it is, but the perception is that you're pushing into the back of the seat, because of course the car's moving forward. Because your body's inertia resists the change in motion. Okay. So there's also some other situations like that we can look at that come as a result of Newton's first law. So we're going to use Newton's first law to explain the following situations. You're sitting in a car at a stoplight when a vehicle rear-ends your car. You're wearing a seatbelt. Describe the motion of your head. Okay, and this is why headrests. So we're going to come back to headrests here and talk about this in a second. Okay, so you're wearing your seatbelt. Your seatbelt prevents you from continuing to move forward if the car that you're in comes to a sudden stop. But being rear-ended is a different kind of accident, right? So you're sitting stationary, you're sitting at stoplights, the car isn't moving. Okay, so your body wants to stay at rest. You get, let's see if I can draw this as a diagram. I've never tried to draw a diagram here before. It's kind of tough, actually. Well, you're sitting stationary, like this is just going to be, don't know where to start. Let's draw the seat. Okay, so there's the seat, yeah. This is probably not going to turn out too well, but so wherever your head is in the seat, like let's just say this is sort of where your body is there. You're sitting there kind of stationary, and a car comes along and rear-ends you from behind. So you feel a big force from the back end of the car. What that's going to do is it's going to push your body forward. So your body is pushed forward. But your head is quite heavy for what it is and for how big it is compared to the rest of your body. Your head is actually pretty heavy, and your neck is actually pretty spindly for holding it up. So it's just like this tiny little kind of tree trunk with a big giant tree on top of it, for lack of a better description, to kind of get you thinking about it. But as your body is pushed forward, your head wants to stay where it is. Your body is pushed forward, but your head, which has more inertia, doesn't follow right away. What actually happens is your body moves forward, your neck comes forward, your head snaps back and then forward. Your neck snaps your head back, and forward quickly. So what this does, this is where, this is what causes whiplash. And whiplash is not an easy injury to recover from, nor is it an easy injury to get any insurance money from. You can be in pain and debilitated by whiplash for years, but because it's what's called a soft tissue injury, most insurance companies don't pay it out anymore because it's also really easy to fake. So the way that you can prevent whiplash in rear-ending accidents like that is by having your headrest adjusted properly. And you want to have no more than about 3 inches between the back of your head and your headrest, and then no more than about 3 inches from the top of the headrest to the top of your head. Most of us are driving around with our headrest far too low for where our head is, which means it's not doing the job it's supposed to do. The headrest isn't a place to rest your head while you're driving. It's meant to prevent whiplash, because if that headrest wasn't there, your head would snap right back on your neck. Okay, and whiplash, it's stretching all the tendons in your neck, it's stretching everything in your neck, and you want to prevent that. Okay, so let's move away from the car accident kind of stuff, which is always a bit of a downer. You're running at a constant velocity of 10 meters per second when you throw a ball into the air, and a few seconds later you catch the ball. Okay, so what's going on here is that if you're running, okay? You're moving forward at 10 meters per second. Whatever ball is in your hand is also moving forward at 10 meters per second. So even when the ball is thrown up, when you throw that ball up, it's still moving, even though it's moving up and then down again, it's still moving forward at 10 meters per second, so that by the time you move ahead, whatever distance you're going to go in the 10 meters per second, the ball also makes it there as well, and so then it's there to fall back into your hand. Okay. We'll try something like that. We'll do a little bit of work with something like that on Monday when I come back. Okay, we're going to switch gears a little bit to Newton's second law of motion, which was our formula. Okay, so this is the one that actually has a formula that we can calculate stuff with. When we do calculations for Newton's third law, we're using Newton's second law to do it. So the formula is acceleration is equal to F net over mass. This is on your formula sheet. It's under the section called dynamics, which is just below kinematics, which is what we just finished doing. A obviously is acceleration, excuse me, in meters per second squared. F net is the net force. In newtons. And M is mass in kilograms. So we have two situations here, and I'm going to teach you something here, though we probably won't work with it until Monday. So actually, no, we'll come back to it. I won't do it today. I'm a little concerned about time. We have a couple things we can say. If the object is moving, like if an object is already moving and a force is exerted on it in the same direction of motion, then the object will speed up. When a force is exerted in the direction opposite of motion, so this would be like friction, the object will slow down. So for now, the calculations that we're going to do with Newton's second law are actually pretty simplistic. We're just going to work with that formula. We're not going to do much more with it. It's when we get into situations where we have to do vector addition of forces in order to find our net force that the calculations become a little bit more involved. But for now, we'll keep them simple. So we have a net force of 18 newtons north acts on a 15 kilogram object. What is the acceleration of the object? So we want acceleration. We have a net force of 18.0 newtons, and we have a mass of 15 kilograms. We're only dealing with a northward force. We don't have any other direction, so we can keep north positive. So acceleration is equal to F net over mass, which is 18.0 newtons divided by 15.0 kilograms. So that gives us an acceleration of 1.2 meters per second squared north. I'm going to sneak in another zero to have my 3 sig digs. Okay, fairly straightforward calculation there. We'll try one where we have to do a little bit of work with kinematics first. A 64 kilogram object accelerates uniformly from rest to a velocity of 16 meters per second east. If the object's displacement during that time is 50 meters, what is its net force during this acceleration? So we have mass is 64 kilograms. We have it accelerates from rest, so VI is 0 meters per second. It accelerates to a final velocity of 16 meters per second. It has a displacement during that time of 50 meters, and we want to know F net. Okay, so to find F net, we have acceleration equals F net over mass. So F net equals mass times acceleration, which is going to be 64 kilograms times some acceleration that we don't have yet. So what we have to do is use this information we have here to find acceleration. Okay, so we're going to use a kinematics formula. So we want the one without time, which is Vf squared equals Vi squared plus 2AD. So Vf squared minus Vi squared divided by 2D will give me acceleration. So now those of you that are comfortable with algebra, you can either calculate out the acceleration and then plug it in, or you can just actually take this whole expression here, and fill it in for acceleration, and then just do one calculation. I'm going to do it separately. So we get 16 meters per second squared minus 0 meters per second squared divided by 2 times 50 meters. And we just want to be careful. We don't have to put in the minus 0 squared into our calculator. We just want to be careful that we bracket the bottom and tell it to divide by 100. Okay. So this gives us an acceleration of 2.56 meters per second squared, and that was east. So I'm going to plug that in here, 2.56 meters per second squared, which will give, and then times that by 64, which gives me a net force of 163.84, or I'm going to round that to 164 newtons, and that's east. I'm going to leave it at 3 sig digs, even though I really need 2. Example 3, and then the stuff with gravity and the normal force and Newton's third law. We'll carry on with this on Monday. Okay, that's the lesson for today. Your sub will give you the handout, the new work booklet for you, and I think it's questions. Well, I can't remember the page numbers because I'm recording this in a different classroom, but I know that it's questions 1 to 9 is what I wanted. It's really just the first section of the work booklet. Yeah, hope you guys have a good weekend, and I will see you on Monday.